Hi, Jose.
Hello.
Hello.
So, what's the plan for right now?
Um, um, I'm suggesting let's start with doing a couple of problems on Bernoulli's equation.
Okay.
Then let's move on to doing maybe one or two problems on buoyancy.
hmm
And then let's do okay. Let's start there, and then see if you have any other questions.
Okay.
So let's start. Yeah. So start with problem 16 on the additional problems in fluids.
Okay. Professor, what is Q is equal to 2.08 CFS?
CFS is cubic foot per second.
Cubic foot per second. Okay.
How's it coming along?
Right now I'm stuck on why they gave me diameter. I'm assuming they gave me diameter so I can find the volume and then get density.
No. What is the other? When Bernoulli's equation, there is another equation that is commonly used along with it. What is that?
Another equation that's commonly used with it. Gauge?
No, it's a Q equal to A times V. The continuity is used together. Area times velocity is the flow rate, volumetric flow rate.
Okay.
So have you all written down Bernoulli's equation?
Yeah, I have.
Okay,
Yeah. No one else has a mic on.
okay, that's fine. So what is it that you are looking for here?
We're trying to find the pressure at 2, P2.
Okay, and what are you given?
We are given the
I
pressure
mean,
at 1. Huh?
uh-huh. Yeah,
Uh, we're given Q so we can solve for either A or velocity. Oh, we know we need to solve for velocity.
uh-huh,
Let's see what else. We know the height.
uh-huh.
So we also know that it's under atmospheric pressure, but because they're both open at the ends, they're gonna cancel out.
No, it's not.
Oh, it's not?
Uh-uh. Because the pressure here is given to be 65 psi, so it's you're doing a balance between one and two. Then one and two are not open into the atmosphere.
Oh, okay.
I mean, the pipe has just been cut. It's not. It doesn't mean that it's open.
Okay. Yeah. So we can solve for V, which is the other variable we don't know,
Uh-huh.
and just solve for P2 because we
Yeah.
we have everything else.
Right. So you can do that.
Yeah. It's just you said the Q is a cubed feet per second.
Yeah.
Okay.
The one thing that you need to keep in mind in this equation is that when you have this guy here, P1 plus rho V1 squared over 2 plus rho G Z1 equals P2 plus rho V2 squared over 2 plus rho G Z2. This rho and this rho G would be in pound per foot cube, whereas this rho you have to convert to slugs.
Oh.
And also remember that this guy is in psi, which means which means that these are in feet, right?
Yeah.
Oh, okay.
So they all have to be converted to the consistent unit.
Okay.
Okay, yeah. Thank you.
Hmm.
What do we use as the area of this cylinder?
Area is the area of the pipe. The diameter
Oh,
is given 6 inches,
okay.
right? So velocity would be q over a. So for the first one, it is q, which is 2.08 is 0.805 or 4 times 6 over 12 squared,
Okay.
Yeah. Okay.
and then v2 would be similar. right? So you can solve for the rest, right?
Yeah, I can solve for the rest. It's
You
just
don't
floating
need to
point.
do the algebra here.
Okay.
Okay, then let's try. Which one did we do now?
We did 11.
16. Okay, then try 17. Any questions, Zach?
So,
Yes. For problem 12, when there's an orifice, what does that mean? Like, what do you do with that?
Where is 12? 12?
Yeah.
Problem
12.
12?
Problem 12 on the same document. It's a diagram. I don't have it right here.
Problem 12. Yeah, what about it?
I'm just wondering, what is the like that it has an orifice? What does that mean? Is it exposed to the outside, or is it?
Yeah, it's exposed, but that's not relevant because for this problem, it is pressure at A that matters.
Okay. Yeah, I was just wondering if that would even make a difference at all.
It doesn't.
Okay, thank you.
So you're going to try 17, right?
Yeah, I'll pull it up right now. I just had to ask that real quick. Thank you.
It's this one.
Okay. Excuse me. Piece of paper.
Problem 17 on the additional problems. Are you done?
no, I just started doing it right now.
Okay.
Okay, so I have like a rough idea on what to do.
Okay.
It's just that my problem right now is there's a pressure at 2 and I don't know how to find it.
Okay. So is 2 exposed to the atmosphere?
It's getting water out, so yes.
Yes. So yeah.
Oh, okay. In that case, they both cancel out then. All right. Yeah, I think I have it done now.
So what does the balance look like? What do you have?
So I have a pressure ATM plus density gravity height is equal to pressure ATM plus 1/2 pressure density V squared. That's it.
Over 2.
Yeah, over 2, sorry.
So let's see. Where did you set your z equal to 0? Where is it?
At point 2.
At point 2. Okay. And why is the first? Why is it that in the first part you were able to say that velocity v1 is 0? Why didn't you have that now?
Because at point 1 we aren't moving any water.
We are moving water. The level of water will drop, but the point is that
There's no loss.
because this area is so much larger. Remember that the continuity says at a times velocity.
Yeah.
So the area of this jet is much smaller than the area of the tank.
Okay.
And it says neglecting the loss, right? So that's why
No,
as well.
neglecting loss doesn't mean that's
Okay.
not loss. What this means is that because the area of the tank is much larger than the area of the nozzle, the velocity of the water from here is going to be much smaller.
Okay, so it's kind of negligible type of thing.
Yeah.
Yeah, because it is.
Okay.
Yeah, exactly. Because you're also going to square it, right?
Yeah.
Once you have this, you're also going to take rho v squared, so that's going to be even smaller.
Okay.
So that's why you can neglect it. So
Okay.
in these kinds of problems, when you have a large tank connecting to a small nozzle, you can usually neglect the area of this tank or the
Okay.
velocity of the kinetic energy of the water from there.
Right.
Okay, so has everyone got that? So the equation is P1 plus rho V1 squared over 2 plus rho G Z1 equals P2 plus rho V2 squared over 2 plus rho G Z2. Here, this is atmosphere, this is 0. This is rho G Z. This is atmospheric. This is this we don't know. This is what we want plus 0. So that all that cancels out, and what you're left with is v squared equals 2g z.
Wish there would. Okay. So okay, P1 and P2 cancel out because they're the same, right? Like you
Yeah,
said.
atmospheric. Okay. And then from there you can plug in the numbers. Okay.
Yeah.
Let's do the next one. Problem 18.
Okay. Figure 10. Bless you. Figure 10 is. So it's. Oops. Uh, hmm.
Okay.
I'm stuck on how to find the velocity at 2.
Yeah, me too.
So, but you got the velocity at 3.
Yeah, I know how to do it. I haven't calculated it, but I know.
You know how to do it?
Yeah.
Okay. So, is there a relationship between the velocity at 2 and the velocity at 3?
Are they the same diameter?
Yeah.
Then they should have the same velocity, right?
Right.
Okay.
Oh, okay.
Let's cancel. So when it comes to finding 3, for the height, which would have the height of 5 meters? Would we put the height of 5 meters at 0.1 or 0.3? 0.1, my bad.
Huh?
When we
You
point,
can put it above, can't you? Well, not above. You can choose either or. That's what I meant.
yeah,
Sorry,
but if you
what is your
do,
1 and what's your 2? Are you doing your balance between 1 and 2?
no, I moved on. I was doing 1 and 3.
1 and 3. Okay.
Yeah. And just wondering, for the sake of speed, is it okay to use gravity as 10?
Yeah.
Okay.
Okay, I'm ready.
You got the whole so
Oh, you went. Wait. No, I have an error. Nah.
I'm gonna grab my calculator real quick. Okay. Jose,
Yes.
for V3, what'd you get?
I got 10 meters a second.
Okay, good. That's what I got. I'm just
what do you get?
10
10
meters.
meters per second.
Yeah, something like that.
Okay.
For point 2, what do you have for pressure of 2?
For me?
Yeah.
I'm just now starting number 2.
Oh, okay. Because
I'm a
I'm
little
not
behind.
really sure how to get pressure 2.
Okay.
What did you get? Did you get it above atmospheric or below atmospheric?
What was that?
Did you get something above atmospheric or below atmospheric?
Who, me or Jose?
Jose,
No, for pressure 2, I don't know how to solve for it.
how do you know? What do you mean?
I'm not sure what the pressure at 2 is. Point 2.
What did you get?
No, I'm saying like I don't know like what to do for it. Like, do we set 1 and 2 equal to each other and then use velocity of
Yeah,
point
same
3?
thing again. Yeah.
Oh, you can do that? Okay, I wasn't sure.
Wait, what?
If you do Bernoulli's
Professor,
equation between
your
1
voice
and 2,
kind of cut out
it's
for me.
conservation of energy, so you can set it across at any 2 points.
Oh, okay.
Professor, your voice cut out when you said how to find 2. Can you repeat that, please?
Yeah, you're just doing energy conservation here. Bernoulli's equation is energy conservation, so you can
Okay.
take any 2 points and set them equal. Energy at this point is equal to the energy at that point.
Okay. And the V3 is equal to V2, correct?
V3 is equal to V2.
Okay. What am I finding? Excuse me. The pressure point. Pressures. What is it? What unit are we in? Meters. Jose,
Yes.
for P1, what do you use?
Oh, ATM.
Okay.
Yeah, atmosphere because it's exposed to the air.
Yeah, like what number value though? Like.
Oh, 101.3, I believe. I think
Okay.
that's it, right?
Oh, that's what I used. I just wasn't.
Trying to stop for P2 right now, but I'm getting a really crazy value.
Okay, I'll catch up to you in like 1 second.
Okay.
I'm just writing it out. Okay. 10 squared. Am I cutting in and out? Just wondering.
No.
Okay. Because they just fixed my router, so. Not the router, the Ethernet thing.
Are we done?
Yeah,
Almost.
I'm stuck. So
Why are you
Okay.
stuck?
I'll be calculating it.
I'm getting a calculation error. I'm getting a really crazy value for P2,
What are you getting?
like something in the thousands.
Well, it's going to come out in like kilopascals, right? The numbers are going to be large.
Oh, really? Okay.
Yeah. I mean, atmospheric pressure is 101 kilopascals, so everything else is going to be that large.
Oh.
Is that right?
What'd you get?
I think I did something wrong because I got a negative.
That's fine. It should be negative.
Oh, really?
Oh, it is.
It should be negative because the pressure here, if this is the pressure here is atmospheric.
Oh, right. It's lower.
It's going to be lower, right?
Yeah.
It has to be lower than atmospheric.
I got. Let's see how many sig figs are there. So I pretty much got around 57,000.
57 kilopascals?
Yeah.
57? I think you got like.
I got something else.
What do you
Yeah,
get?
See, I got 1, 2, 3, 4, 5.
I
I got
might have.
3.52 to the 5th power.
Let me put that in engineering real quick. My bad. Yeah, negative 57 times 10 to the third.
Uh, so, okay, so let's see. I think you might have a calculation mistake, but I'm not sure.
Okay.
So what you got velocity v2 as a v3 as?
That's 10 meters per second.
10 meters per second.
So that is the same as v2, right?
Yeah.
Yeah.
So pressure, so energy at 1 equals energy at 2. So P1 plus rho V1 squared over 2 plus G rho G Z1 equals P2 plus rho V2 squared over 2 plus rho G Z2. That is atmospheric. This is 0. Let's take our reference plane here. So that's 0. P2 here is P2 plus rho V2 squared over 2 plus rho G times Z, where the Z is 2. Alright?
Mm-hmm.
So I get PA equals P2 plus rho 10 to the 3. This is 10 squared over 2 plus this is 10 cubed, this is 10 and this is 2.
Okay.
So that is P2. This is 100 squared is 50. 100 squared 10 squared is 100 divided by 2 is 50. So 50 times 10 to the 3.
Oh, okay. I think I see where it is.
So it should be P2 plus 70 kilopascals.
I see exactly what it
How are
is.
you getting 10 to the 3? Are we dealing with water? I thought we were dealing with oil.
Is this oil? Okay, then it's
Yeah.
0.2. That is multiplied by 0.82.
Yeah, I see what I did because for the PGZ1, I used 5 meters because I was still using the bottom as my reference. So that's where I went wrong.
How did you get 50?
10 squared. 10 squared over 2.
Oh, yeah. Okay. Sorry.
Okay, I see where I went wrong then. So it is a negative though, right?
Yeah.
Okay.
Can you move the paper up? I can't see the...
Yeah, the names.
Yeah, the names and pictures are blocking the bottom portion.
Now?
Yeah, I can see
Yeah.
now.
Thank you. Okay,
This
so
is subatmospheric, right? This is below atmospheric.
0.
So P2 minus PA is negative 70 times 0.82 kilopascals.
Oh, I know what I did wrong.
What'd you do?
I forgot that it was kilopascals. I thought it was just pascals.
Oh.
Yeah.
Okay.
Oh, good thing I realized now.
Yeah, better now than on the final exam, right?
Yeah.
Right?
hmm
Okay, then try the next one.
All right, let me get a new piece of paper real quick.
This one.
Okay. Oh, that's a weird diagram.
Yeah.
I don't think I've seen one like that before. Just wondering, how would a pipe like this work?
What?
Like, just the way it's set up. Like, what is it for?
It's for measuring the flow. You'll see. Do it. You'll see why it's used.
Okay. I was just curious.
No, just do it. You'll find out.
Okay. And flow nozzle, A2, B. Get everything. 1, 2, HHG, A2. AB flow nozzle. Okay. Oh, I was reading the wrong one for a second.
When it says to determine the discharge, is it telling us to find Q?
Yeah, discharge is Q.
Okay.
To find what? I can hear you.
Oh, Q.
Q? Oh, okay.
Turns out area. Hmm.
Oh. Hmm.
Yeah, I'm stuck on how to do this problem.
Yeah.
Gonna be honest.
Did you do the do the energy balance?
Yeah, that's the thing though.
I don't.
Just between A and B, do the energy balance.
Ignoring the.
Yeah, what does the equation look like?
It's gonna be P of 1
Problems
plus.
in one. This is the two problems in one. There is a manometer problem below, and then above that is your regular Bernoulli equation.
What does the manometer problem solve for, though?
You'll find out soon enough.
Okay.
So
Just trust.
All in due time.
just do Bernoulli's equation first. You'll find
Okay.
out.
Would the height be negligible since there is no change in height?
Yes, there's no change in height.
Okay.
Yeah, okay, that gets rid of that then. Are the pressures going to be the same?
The what?
The pressures?
Absolutely not.
Oh, because the. Right.
Look at the manometer leg. Look at this.
Okay.
Which means there's a higher pressure on the left.
Oh.
Yeah, because the A is pushing it down, so the manometer has gone up.
Oh. Oh, I think I know how this works. Okay. I think. I'm not going to say I do.
So,
It's negligible. P1 is greater than P2.
mm,
Ah. The reason the manometer is different is because as it goes through the smaller diameter, the pressure decreases as the velocity increases, right? And so that's why there's a difference.
The other way around. Hold on. As the area decreases, so the diameter decreases, what happens to velocity?
Goes up.
What happens to the pressure?
Goes down.
Goes down.
oh.
Yeah.
Because the sum of pressure and velocity and
Oh.
kinetic energy has to be the same.
Yes,
Mhm.
yes.
When the kinetic energy goes up, the pressure has to go down.
Okay.
And that is why the pressure here has to be
It's
lower.
lower.
There.
Okay.
And that's why the manometer is able to, this fluid is able to push it up here.
Okay. Yeah, I just wasn't sure if that would be what happens, but. Excuse me. So what exactly are we? Oh. Whoops. Let me go grab some. And this. Oh, that's cool.
What is?
I just read the comments.
Oh yeah.
I've always wondered that's how it keeps flowing.
Yeah.
All right.
It won't flow initially. Remember, it won't just flow because there is no gradient to push it up from here to here.
Mm-hmm.
Once it starts flowing, it'll keep flowing.
Yeah, it won't stop until it reaches the bottom of the tube.
Yeah.
Okay.
Yeah.
That's interesting.
Yeah, I know.
It's still stuck though.
What are you trying to find?
Well, we're trying to find the flow rates. So
How far are you? What did you do?
I found P1 using the manometer.
No, you cannot just use. You cannot find just P1.
No?
You can only do P1 minus P2.
Huh.
I don't know how you found P1. So tell me your equation. Tell me your procedure.
I think I know what I did wrong. Well, what I had originally was I did the manometer problem, and I set it pressure equal. Or I set two equal pressures to that point towards H, and from there I did.
No, first start with in these problems. Start with Bernoulli's equation first, because that will tell you what you need.
Yeah, I started there, but I didn't know where to go.
Yeah.
Okay, what did you do? So tell me what you did.
I just wrote out Bernoulli's equation. I took out the PGZs because there was no height difference.
Mm-hmm.
All right, and then
I put P1 minus P2, and then I put the 1/2, and then I put the PV squared over 2 on the other side.
Okay, that's good. Now while you're there, what is the relationship between the velocity here and the velocity here?
VB is greater than VA.
And and what's the what? Yeah,
VB is greater.
Oh, and what's the relationship? What is actually a mathematical relationship between them?
There is.
Yeah, whatever's flowing here has to flow out through that.
You have to use the diameter. You have to use the area of that, the surface area of that, whatever that is. That's A2.
Uh-huh.
You have to use the surface area of that, like that whole equation type of thing, and then you get the velocity there, and then you could have it.
What's the relationship between these two velocities?
Let me pull it up. Let me.
The discharge here has to be the same as the discharge here, right? The flow rate here has to be the same as the flow rate here.
Yeah.
What's the flow rate here?
The area times the velocity.
Which has to be the same as the area times the velocity here.
Yes.
Yeah.
That gives you a relationship between the velocity here. If you know the areas, then you know the relationship between the velocities.
So they're going to be the same?
No, they cannot be the same. There are different areas.
So.
1 second.
You would be able to find the mathematical relationship to it.
I think you're overthinking this. It's here.
I probably am.
A1 V1 equals A2 V2, right?
Yeah, that's what I've written down right now.
So V2 is equal to A1 over A2 times V1. That's all. That's the relationship.
Oh, that's all it is?
Yeah. So then you have a term that looks like this, right?
Yeah, on one side of the equation.
And plug that in there. You'll get in terms of V1.
Okay, and then you could solve for V1 from there.
Yeah, and then you can solve for V1. So then once you're done with that, the only thing you don't know yet is P1 minus P2.
Yeah.
Right? Everything else. Now, how do you find P1 minus P2? That's what the denominator comes in.
You could do the PGZs down there. Right?
Exactly. Yeah.
Okay. And it would only be the PGZs and the P1 and P2?
Yeah.
Okay. Right. So it's pretty much using two different systems to bring them into one, right?
Yeah.
Okay.
What exactly is P1 minus P2? Are you subtracting it from the Bernoulli equation?
Sorry.
You guys were saying that you were doing P1 minus P2. What is it
Yeah.
exactly?
It's from the Bernoulli's equation. If you do
Oh,
Bernoulli's equation, you get it.
subtracting it then.
Rearrange Bernoulli's
You
equation.
just move them around, and then you get it.
All right. Just making sure.
Okay. Okay. There. To find this system. Plus H. Would they both have the rho GH on, or would only one side have the rho GH?
What rho GH?
For when you're using the manometer or whatever it's called, the name is.
Well, with this one.
Yeah, the small tubing, whatever manometer, right?
Yeah. So you have to. So in these problems, you're always equating the level at some point, equating pressure at some point, right?
Okay, so it's zero at some point.
Yeah, you have to set. You have
Okay.
to set the pressure level at some point.
It's like using the gravitational potential energy. You got to set the zero somewhere, and then you could use
No,
that.
no, not somewhere. You have to set it where. You have to set. This is a regular manometer problem. So
Yeah.
you have to set it at the same level of the same liquid.
Yeah, that's what I meant. I didn't mean like anywhere, but that's just how I was
Right.
referring to it.
Yeah.
So it'd be P1 equals P2 plus rho GH.
What?
P1 equals P2 plus rho GH.
Yeah, P1 equals P2 plus rho GH. How did you get it?
Well, I set the zero at the height of the number one side. So it ended up being P1 plus, well, the velocity is negligible there. So that's zero. The rho GH, since I set that to zero, the H is zero, so it just
So
be
you
P1.
said this is zero?
Yeah.
Okay.
And then equals P2, and then again the velocity is negligible. And I did that plus rho GH.
Wait, you did Bernoulli's equation again?
Yeah.
Between what point and what point?
1 and 2.
1 and 2?
Yes.
Going through like that?
Yeah.
But the fluid is not flowing like that. There is a column here. Bernoulli's equation only applies when the fluid is flowing, when it's the same fluid.
Okay.
You cannot cross. I mean, you're right. I mean, the answer is right, but I think you got it.
But the way I got it's wrong.
Yeah.
Okay.
So let's take this level here, okay?
Okay.
That's zero?
What is let's call this C prime. What's the pressure at C?
It's pressure of 1 plus PGZ, which is 0.
Whatever this is. Right?
Yeah.
Yeah.
And what is the pressure here at C prime?
Pressure B? So pressure 2?
Let me okay, Z. Pressure at 2.
And plus that small, plus the height of that, and also the height above 2.
So what is this height? If this is H and that is Z, this is Z minus H, right?
Yes.
So it will be pressure of rho
Okay.
Z minus H plus this column. Pressure of
Yes.
this is mercury H times G. So it will be P1 minus P2 equals this cancels out. So all you get is P rho G minus P rho times H times G.
Hmm.
Right?
Yeah.
And then plug that into that other expression that you had for V2 V1, and
Okay.
then you're done.
So,
Um,
what was the relation between the velocities again? I wasn't there for that.
It is so let me solve this
Okay.
because it's kind of useful. Okay, so that is 0 because V1 equals Z2.
Yeah.
Okay, and then I can write P1 minus P2 equals rho over 2 V2 minus V1 V2 square minus V1 squared.
Yes.
By continuity, A1 V1 equals A2 V2, which is Q.
yeah.
The volumetric flow rate through the system is the same, so A1 V1 equals A2 V2.
Hmm.
So from this I get V2 is A1 over A2 times
Oh,
V1.
okay.
So then
Yeah,
I
and
can
then
get P1 minus P2 equals rho over 2 times A1 over A2 V1 squared minus V1 squared. So this gives me rho over 2 V1 squared A1 over A2 squared minus 1. So that V1 equals 2 times P1 minus P2 over rho 1 over A1 over A2 squared minus 1. Good?
Yes.
Now we need P1 minus P2. So let me draw that thing again.
Can you lower the paper?
Raise it, you mean? Okay.
Oh, sorry, raise it.
yeah.
Actually, it should be, I should have put it here. Okay, fine. So this is velocity V1, velocity V2. Okay. So here is the mercury.
Dining
So
hall.
let me call this Z, and this is H. This is given to us. This H is given. So that the manometer part of it is, so let's call this C prime. So pressure at C equals pressure at C prime. Pressure at C is P1 or PA, same thing. P1 plus H rho Z, and that equals pressure at C prime, which is pressure at 2 plus the pressure of this column, because this is Z minus H, and then plus H mercury, rho mercury times G. So that P1 minus P2 is Hg minus this is H G times rho Ag minus rho. So now I take that and plug that in there. I get V1 equals 2 and there is a G somewhere, Ag, sorry. Alright. And so Q, the discharge, would simply be A1 times V1.
It's funny when you put it all together, it looks really complex.
I know, right?
It's one of those things where the work leading up to it's like, oh, and then you get
So beautiful.
Yeah, but you can recognize it, but look at the terms. 2GH, the square root of root 2GH. This is showing up everywhere. Remember, we had this in just about every problem, square root of 2GH. And then there is something here that's multiplying, and this has no units. Right? Density over density minus 1 is no units.
Yeah.
This one is A1 over A2, no units. So
Yeah.
there's a unitless quantity here, a unitless quantity here, and it's multiplying square root of 2GH. So and Zach, you're asking why you would use such a thing. Because you can measure the velocity by this method.
Yeah.
All you need is a manometer, and you put an orifice plate here. So you measure the pressure between outside the orifice and after the orifice, and then you measure this height, which is easy to measure. If you measure the height, then you can use this formula to find what the Q is.
And that's an easy way to find the velocity of the flow?
Yeah, this is the standard. This is one of the standard ways to do it with an orifice.
What is the reasoning behind finding velocity? Like, what can you use that knowledge for?
To like, let's say the water company wants to charge you for how much water you use. You need to know the flow rate, right?
Yes.
Oh, and that's how you measure it.
Or you're pumping gas, and you want to find out how much gas you used.
Oh, is that how the meters work?
Though they use turbines, but it's a similar principle.
Okay.
Huh.
Okay.
Everyday
This is
application.
similar.
Yeah.
This is similar.
Where's that?
This is the next problem.
Going into? Is that going into the side of the tube? Like, does the orifice carry around to the side of the tube?
This one?
No,
Here?
no, I'm talking about the one you just showed us.
This one? No,
Yeah.
this is not. No, this is not orifice. This is just a tube that is just stuck into the flow.
Is it connected to it?
Yeah, it is just a tube that is stuck right into the flow.
Okay, thank you.
This is how, by the way, all airplanes measure velocity of wind. If you want to know how fast the wind is flowing through an airplane, this is how they do it. There is a little. If you look at the front of an airplane, there'll be a little tube that's sticking out of it.
Yeah.
Look closely next time you fly. It'll be there. On the front of the plane.
That's on every plane?
Yeah, all planes have it. It's called a pitot tube. So
wait, is P2 out of the system, or is it inside of it?
It's right inside the tube.
Okay. So it's going.
Yeah, it's here. You can assume it's somewhere here.
Yeah. Okay.
Wait, there's a question by David. Sorry, you mean this one? No, that's not a mistake. It is the pressure here, which is the pressure at 1 plus h rho times z.
Okay. Well, flow is problem 20. Professor,
Uh-huh.
after this one, if you don't mind, can we do like the elongations from the strain and stuff like that?
Sure.
Okay.
In the diagram, there is another type of liquid or fluid in the manometer part, right?
Yeah. Yeah.
Okay, just making sure.
It might be mercury. I haven't read the problem.
I don't think it.
Oh, it says mercury.
Oh yeah, mercury.
My bad.
Exactly. Loss to the flow rate. Flowing fluid is water. Excuse me. Wait.
Uh-huh.
I was just looking at what Alex said. For what problem is that?
This is on one of the practice. What's that thing called?
Oh, okay. I was like, how did he get watts for?
Uh,
It's kind of thrown off for a second.
you get?
I'm still working out the problem. It's the same procedure though as the other one.
Yeah.
I will be back. How goes it?
My mic was off. I have it down. It's just plugging in the values at this point.
Okay, so tell me what you did.
So the first thing I did is it's a Bernoulli problem. So I said P1 equal to P2. So P1 plus PGH plus PV squared over 2 is equal to P2 and the same thing. But and then the PGH ends up canceling out because it's equal to 0. So you can
What is
ignore it. Huh?
what is
PG height, uh,
P?
density, gravity, and height at point 1 and 2.
I see the okay, the potential term. Okay.
Yeah,
Mhm.
yeah. And then from there you get
What is V2?
P1. Huh?
What's V2?
What was that?
What's V2?
Oh, V2. V2. V2 is equal to. I saw for V1, but V2 is equal to V1 A1 over A2.
No, but V2 is stopped. See, there's nothing. It cannot flow. There's no flow here.
I thought I was going the other way though.
No, but inside the tube, there's no flow, right?
Oh, I didn't know that.
Yeah. Well, I mean, once it's inside the tube, there's a manometer fluid here. How can it go any further? It stopped.
Oh, huh.
And so because it stopped, velocity v2 is 0.
That changes my problem completely. Dang. Oh. Yeah, that's a big error on my part. I didn't think of that.
Yeah, all you have to do is in these problems is to look at each term and see what the values are one by one
Yeah.
after the other.
But at one there will be a velocity though, right?
Uh-huh. But yeah, one yes.
Okay, just not a two then. Okay. All right. Well, in that case, I can just get rid of V2. Okay. Well, because of the error, I have a weird equation trying to fix it. But yeah, I get the general idea of it, and I think I could do it if I were to rework the problem again.
All right. I mean, the solutions are posted, so you can look it up.
Oh, they are. Okay. I didn't know that.
Okay. Let's try. Okay, so let's. I don't know where Zach went because he's the one who wanted to do some stress strain problems. But let's do number 11 from here because that kind of combines buoyancy with stress.
Okay. Professor, so in problem 11, there is a force buoyant going against this sphere.
Yeah.
Uh, and the equation for force buoyancy is gravity, the density, and volume, right? Correct?
Yes. Yeah.
What volume do we use? Do we use the volume of the circle or the volume of the container?
Volume of the water displaced.
Oh, the water displaced. Okay. I'll be right back. Okay, I'm back. So I still haven't. I was just starting problem 11, but Professor, are you there?
Yeah, I'm here.
Okay, so my idea on how to solve it would be first we need to calculate stress, and by doing that we need to find the force buoyancy because that's going to be the force acting on the chain, and we're given the diameters and we can find the area that way. We find the stress, and what else from
Right.
there?
Right.
Yes, it's asking for factor of safety. Okay, so it's asking for factor of safety. We know the yield strength, and we now calculated the stress. So from there, we can get factor of safety.
Right.
What else is there? Also, how much does the rope stretch? So since it's uh, vertical, we want to find the vertical stretch, which would be change in it would be epsilon is equal to change in L over L, correct?
Right.
Okay. And then for change of diameter, you could use Passion's ratio or constant. It's the V. I don't remember the actual name for it. Is
Yeah.
equal to delta D over epsilon.
Right.
Yes, and then from there you can find that,
Yeah.
and that's how you do the problem.
Right.
Okay,
But do the first part of it.
okay. So still want me to do it then?
The first part. Yeah.
Okay. For for finding a force buoyancy, do we use the density of the steel or the density of water?
You tell me.
I would think that's density of the steel, because we're finding the displacement volume.
What is the buoyancy force for? The buoyancy force is from where? It's from the fluid.
Yes.
So does it make any difference whether you put a steel ball or a ball of wood or gold?
Oh no, it does not. Okay.
It's basically from the fluid. All that matters to the fluid is how much volume it's displacing.
Yes. Okay. It's volume. The volume of a sphere is 4/3 pi r cubed, correct?
Mm.
Okay. I'm looking at right now at the solution for 11, and in it you have 4 pi over 3 multiplied by 2 to the 3 minus 1.99 to the 3.
Yeah,
Why do you have 1.99 to the 3?
that's the mass of the if you want to find the mass of the ball,
Mhm.
that's what it is because it's a hollow ball.
Oh, okay. Okay. All right. Oh, Professor, I also have a question on what is it? What is it? Bank, like the angle of a bank.
Huh?
I also have a question on the bank angle.
Yes.
Okay, so for bank angle, we usually divide both equations and get tangent theta. Why can't we solve for it using like sine theta or cosine theta?
Do that.
Huh?
You can do that.
Oh, you can. Okay.
Yeah.
Oh, I had a question for this, actually.
That's normally how I do it, but you can do it. You can solve it in any way you want.
Okay.
For this diagram, does it apply to number 9? Or
What are you doing? Which one?
figure 3?
No,
Is that?
that's for problem 10.
Yeah, I know, but like, is it right for the corresponding problem for figure 2?
Figure two. I don't know. I mean, I think I messed up. It's not for the same problem.
Yeah, I was like, that does not look like a hydraulic jack.
No, it's not.
Okay,
I
thank
was
you.
trying to solve it and I couldn't figure out what I was doing either. So this one is correct.
Yeah, I tried applying it to the bottom number figure 3, but yeah, I just wasn't sure.
So Jose, which one are you going to do? What are you trying to do?
Right now I'm thinking of what other questions I have
Okay.
because
Yeah.
for that problem the part that was throwing me off was the 1 point. It was the fact that it was a hollow.
Yeah.
That was hollow. That was throwing me off.
What part of it?
So for the steel ball, it's actually hollow. I didn't know how to put that to the question.
For number 11?
Yeah,
Okay.
because for the other stuff, it's just what we've been doing, finding everything else.
Mm-hmm.
From there, it's just equations and plug and chug.
Okay.
Yeah.
Yeah, because I missed that whole part.
Oh, okay.
So I was just trying to catch up.
Yeah. So right now, I'm looking for like, additional questions I have.
Sure. Go
Okay.
ahead.
Can we do that? The strain stretch
That's
thing.
what I was trying to
Oh,
do.
yeah, that's what this one is, dude.
Oh, it is?
Yeah, this one involves fluid dynamics and or fluids and also stress.
Oh, it's got both.
Yeah, it's got both.
Wonderful.
Best of both worlds.
Yeah. Um, so when you're using specific gravity with a solid, is it still times the density of water, or what would you do
Yep.
for that?
Same thing.
Okay.
Same thing. Why would you want to change the definition midway?
No idea, just making sure.
No.
Wait, so it has a lateral stretch in it too?
No, just a tensile.
Right. Okay, we have something that does like the lateral strain. The
This one does. There's lateral strain here too.
I mean like the stretching of a material, like the changing of the length and diameter. Like
Yeah,
Yeah.
this one has that.
it does? Oh, my bad. Oh, my bad. Think I was reading the wrong one. Let's see.
What's the first thing you're gonna do for these problems?
Free body diagram.
Yep.
Always free body diagrams.
Yes. I got confused at first why I got gigapascals, then I realized it's just it's still okay.
For which?
For stress.
Okay.
Wait. Wait, doesn't the steel ball just pop off of the? Yeah, it does.
What?
The For my stress, I got a higher stress than the yield.
Okay. So what does that mean? Which means the cord is broken, right?
Yeah,
How,
the cord breaks and then floats back
so
up.
what did you get for the stress?
294. Oh no, for stress, I got 3.74 gigapascals. Yeah.
3 point something like that. Yeah. Okay. So let's. So then, what would the diameter have to be safe?
Oh, to be safe. Okay.
I mean, it's not part of the question, but I'm
Oh,
asking.
okay. So let's see. Do you want me to solve for it, or do you want me to say how I would solve for it?
No, solve for it,
Okay.
because then we can do the rest of it.
Factor of safety.
Let's say the factor of safety is 2.
Okay.
I mean, it's already broken, so there's no factor of safety.
Yeah. I was wondering if they gave us one. 5 megapascal.
Was that above us? that was you. What? Is he really? Wait, was that next to us or above us? I'll be back. 1 second, sorry.
Yeah.
So the diameter would have to be 0.016 meters.
Isn't this 0.016 meters?
Yeah.
16 millimeters?
Yes.
Really?
Maybe I didn't convert it properly. Oh, so what I did is you said factor safety of 2. So I did 2 is equal to yield over the stress. I found stress to be 22.5 megapascals.
Correct.
And then from there I set it equal to the tension, which would be force buoyant, which is
294, right?
yeah
94 kilonewtons.
294 kilonewtons, and then it's over pi over 4, and then
So,
diameter squared, and it's all for d.
so 294 kilonewtons 10 to the 3 divided by 20 to the 6.
Maybe it's just calculation error.
No, I mean it just seemed a little. I mean,
Yeah. Oh yeah. No, it does seem pretty weird. Because what was the actual diameter?
I don't know. I'm solving it now.
Okay, I'm back, sorry.
So D is 0.13. So 13 centimeters.
Maybe I'm doing it wrong. Maybe I'm doing calculation errors then. Let me try it
Did
again.
you make sure that this is in kilonewtons?
Sorry?
This is in kilonewtons.
Yes. What I did is instead of converting it just to newtons and that to pascals, I set 22 megapascals to kilopascals and then divided by that. Is that not correct?
22 what?
I did 22 kilopascals.
Okay, that's fine. Let's just still give you the answer.
Okay. Yeah, and then I got one. It's 16 centimeters. Hold on. This times.
I'm just gonna wait till the next problem, so that way.
Yeah, I got 1.6 centimeters.
1.6?
Yeah.
So did you get this?
Yes. I think I'm just inputting it wrong then, because I had the same thing.
Do it again.
Okay.
Missing a parenthesis somewhere or something.
But that's probably it.
There's no parentheses, just straight division.
Okay, yeah, now I get it. Yeah.
Okay. So now D is 13. Now let's say the length of the rod is 10 meters. Okay.
Okay.
So now find the extension in the length and the decrease in the diameter.
Okay. Are we gonna use the same?
Yeah, the same. Yeah.
The
I mean,
same.
we have a new diameter though.
Okay, so just a new diameter, and then everything else is the same.
Yeah.
Okay.
Zach, pick some problem
Okay, sorry. I was just waiting to see.
while he's doing it.
Okay.
Ooh.
Let's see. That's so
That's 0.4.
oh shoot. Professor?
Yeah.
Is the Stefan Boltzmann constant 5.67 times 10 to the negative 8?
Yes.
Okay.
What units?
Is that in the? It's in the not. It's not USCS. It's the other one. It's
Yeah, but what units are they?
yeah. Trying to recall. I want to say Newton meters, but I know it's not.
Is heat transfer? How can it be Newton meters?
Yeah, that's why.
Watts per meter squared Kelvin to the fourth?
Yeah, correct.
Oh yeah, because they have to all cancel out. My bad. Well, not all of them, but just because you're going temperature, so 27.
I got change in diameter is equal to 0.56 meters, and change in length is equal to 0.1125 meters.
Okay, so epsilon would have been 22 megapascals over
The
2
2
G.
gigapascal. Yeah.
So it would have been 11 times 10 to the negative 3.
Yeah.
So delta L would have been epsilon times L, which is 11 times 10 to the negative 3 times 10, which is 0.1.
Yeah.
0.11 meters.
Yeah.
Or 11 centimeters stretch.
Mhm.
And now epsilon lateral is nu times epsilon A. So this is 0.4 times 11 times 10 to the negative 3. So it is 4.4 times 10 to the negative 3. That is a lateral strain. And the change in lateral dimension would be epsilon L times D. So 4.4 times 10 to the negative 3 times 13, which gives you something like 57.2 times 10 to the negative
Yeah.
3.
Yeah, I got the same thing.
Okay?
Yep.
For you probably do not have this up right now, but for number 25 on the thermal short problems.
Yeah.
It says the emissive power of a blackbody sphere is of diameter 10 centimeters with a surface temperature of 127 degrees Celsius. It doesn't give us the emissivity. Are we supposed to find that from what we're given with the diameter?
Wait, is it black body?
Oh, there is no. Wait,
Is it a black body?
Yeah.
Black body means 1.
Oh, right. Oh.
That's what it means.
Yeah. I completely blanked on that. All right. Thank you.
I'll be back.
I need to leave in about 10 minutes. Let me. If you
Oh,
have
wait.
any question, let me know.
Wait, you're gonna leave right now?
In 10 minutes, yeah.
Oh, okay. I guess I'll just stay then.
Okay, so common plus 4 cancels it. What is the units for emissivity?
Dimensionless.
Okay. Okey-doke. 2. And you suggest we keep it in engineer mode, right?
Yeah.
Okay. And if we have the chance, always put it down in scientific notation, so that way we don't lose track of zeros.
Right.
Right. Um, Jesus. Mhm. I. mm. Okay, and Professor,
Uh-huh.
if you said to define like the first law of thermodynamics, and we put delta E equals Q plus W, we would define the variables, and that would be considered okay.
You have to state it in words.
Okay.
Also, the second law of thermodynamics is just the two
Yeah, there are two statements.
the two cases that can't happen, right?
There are two statements, yes.
Yeah, the two statements.
It's the Kelvin and the.
Clausius.
Yeah, I can never figure out how to say it. If we attempt to spell it, will you be able to understand?
What?
If we like attempt to spell it, like if we get the gist of. Like
Yeah,
the
yeah.
title. Okay.
As long as you mean the laws,
Yeah.
as long as you have all the elements that are necessary, that's fine. You don't have to regurgitate it verbatim.
Okay. Like
You just have to
because.
get the gist of the law correctly.
Do we need to have the person's name saying like it's this person's statement, or do
Yeah.
you
No,
just write the
it'll
law?
tell you what it'll tell you. State this particular state the Kelvin Planck statement.
Oh, okay, all right.
It'll be specific.
Oh, I thought I would have had to like write the name too.
Yeah.
No.
Half the problem is can you spell it? Can you spell the name of the guy?
Oh my. 90% of the test. Can you spell its name?
So for the second law of thermodynamics, we are doing the Clausius statement as well as the no energy leaves the system, correct?
No energy what?
No energy would leave the system.
That's not the statement of second law. The second law is Kelvin Planck. Kelvin Planck and Clausius.
Okay. What was the Kelvin Planck statement again?
That's the one where you cannot you cannot convert all heat into work.
Okay. Thank you.
Okay. Yeah.
Okay. I cannot believe it's already tomorrow. The final.
Oh yeah,
That was quick.
it was really quick. That's the quarter system for you, though.
Yeah, true.
This week alone, the entire week was so quick.
Yeah.
Not for me.
Really?
Yeah, no, I've been waking up at 4 a.m. every day.
Ooh.
It's long days
Jeez.
for me.
Ooh. Um. And you said to make sure we look over like all the refrigeration cycles and
Yeah, just look through. Yeah, just figure out what the components are. Figure out what each of them does, like each component, like what happens in the condenser, what happens in the compressor, what happens in the boiler, and so on.
okay. And then I had asked you about the nuclear power plant, and the only difference between that and the engine is the nuclear part itself, right?
Yeah, the boiler of the steam power plant.
Yeah, that's replaced with the nuclear reactor, correct?
Yeah, usually you would be burning coal or natural gas, and there
Yeah.
you have a neutral reactor.
Okay.
Otherwise, it's all the same.
Yeah, I remember that being a assessment problem too.
And then also with the engines, how you said to like know the different parts. Will we have to apply like numbers to those different parts, or is it just the part itself?
No. You don't have to know all the parts. So you just have to know the principle.
Oh,
Wait, so we don't need to know the parts of a engine then?
No.
Oh, thank God.
Yeah.
DOHC, man, DOHC. Um, hmm.
You all studied out?
I just making sure.
Yeah, I have no more questions.
Okay,
Yeah,
go on.
Huh? Hmm.
No questions I can think of.
Oh, in your slides you had the like wavelength and radiation for like the
Oh,
spectrum.
Yeah.
Where would we apply that? Because I know there was only one
That'll be a
question on
separate
this.
question. It has to be a separate question. It won't be part of anything.
Huh?
It'll just be an explicit question. What is the maximum wavelength or something like that?
Oh, okay.
Yeah, it's maximum wavelength is equal to the temperature. Make sure it's in Kelvin, I believe, and it's equal to 2,900 micro wave
Micron.
meter, something like that.
Microns.
Microns. There you go.
2,900 microns.
Yep.
Okay. And you said it was equal to what? The heat or something like that?
Yeah, temperature. It has
So-
to be in Kelvin or Rankine, right?
Lambda equals the T in
Lambda
Kelvin.
times T.
Lambda times T equals. Okay. Jose.
Yes.
So it went. What does it equal? Lambda times T equals what?
Lambda max times the temperature is equal to 2,900, I believe.
Like it's not a variable. It's just a definite 2,900.
Yeah, and then microns.
Not microns. Micron Kelvin.
Oh, micron Kelvin. Sorry.
Microkelvin? Wait, what?
Micron Kelvin. Micron times.
Micron Kelvin. I was like, what's a microkelvin?
Oh no.
10 to the 6 Kelvin is microkelvin.
Just like turbojets have turbos, right?
This whole time.
Yeah.
If I only knew.
All right. Anything else? I need to get going.
I
don't
think
so.
yeah. I think that's it. Thank you.
You good?
Thank you.
Okay.
I appreciate it.
Thanks.
See you tomorrow.
See you guys tomorrow. Good luck, everyone.
Good luck.
Guys.
Good luck, everyone. Bye.
Uh,
See ya.
all right. Later.
Bye.